Hello, welcome back. So today, the pigeonhole principle, which is a very cool principle. It's a counting trick. And it's like even it's like a super obvious principle, but it can be very, very, very tricky to apply. Sometimes you can prove some really very cool stuff. And I'm going to show you some today. So here is the basic version of the pigeonhole principle, which I'm sure you will believe. It is this. So if you have k plus 1 objects and you place them in k boxes, then I guess you can guess that there is a box that which will contain at least 2 objects. So there exists at least one box containing 2 or more objects. Okay, so why is it called the pigeonhole principle? Because you're pigeonholes, right? In French, it's called something else. It's the Dirichlet drawer principle. So, le principe des tiroirs de Dirichlet. So I've never seen it called this way in English. It's the pigeonhole principle, but if you read a book in French, it'll be called this. Okay, so he was having a really good day, Dirichlet. So here's a couple of little very, very obvious applications. I mean, hopefully you believe this. I actually have a proof in my notes, but does this require proof? I guess so. I guess we should prove it, but I don't know if the proof is really more than just restating the whole thing. But if you did not have at least one box with 2 or more objects, then each box would contain at most one object. So if each box contains at most one object, there must be at most k objects, right? Which is basically just restating the principle. Okay, so here's how do you use this? I'm going to start with some very, very simple-minded examples. I'll move on to some really not simple-minded examples of use of this. So here's one. If you have a group of 367 people, at least 2 have the same birthday. Right? Because, well, why 367? Because there are 366 different possible birthdays, right? So 366 different birthdays. These are your boxes, right? Because of February 29th, which is a possibility. I don't know if you know anybody born on February 29th. I don't, not personally at least. There's a famous hockey player, but so yeah, so hopefully you believe this. If you don't, just, I mean, interrupt me, obviously. Here's another one. If you have 27 English words, any words, just pick any 27 English words, then at least two start with the same letter. At least two start with the same letter. Because there are 26 letters, think of those as the boxes, and you're placing the words in the boxes depending on their first letter. And since you have one word more than there are boxes, then one box will contain at least two words. Okay, very good. Here's a not so obvious one, which is really cute. It's not really hard, but it's like it's really cute. I really like this example. So for every positive integer n, okay, there exists a multiple of n whose digits are only zeros and ones. Okay, so let's say you take n equals 1,234, then there is a number written with only ones and zeros, which is a multiple of 1,234. If you try to prove this without the hint of the pigeonhole principle, it might be very difficult. Even knowing that you should use the pigeonhole principle, it is not so obvious. So let me show you how this works. It's pretty clever. Okay, so here's the trick. Okay, so we have a number n, and I want to find a multiple of n which can be written down with only zeros and ones. Okay, so here's the trick. Consider the following numbers. 1, 11, 111. So I'm going to list numbers which have only ones as digits, right? And I'm going to take a lot of them. What's a lot? I want to take actually n plus 1 of them, which means, well, this first one has 1 1, the second one has 2 1, so this one here has n plus 1 ones. So that's a total of n plus 1 different integers, right? Okay, from this point on, I could actually leave it as an exercise, and I think many of you, if not all, would figure it out. It could take a while or not, but this is really the key point. Okay, so I've got n plus 1 different integers, which are all written with only ones. Okay, now I'm not claiming that one of these is a multiple of n. It's not true, but think about the division of these numbers by n, remainder. So consider the remainder of division by n of these numbers, right? So what are the possibilities? 0, 1, right up to n minus 1. So there are n possibilities. Everybody agrees with this for sure, right? Division algorithm. So if you divide any of these numbers by n, you look at the remainder, it is a number between 0 and n minus 1. So there are n possibilities, and we have n plus 1 numbers. Pigeonhole principle says 2 of them must have the same remainder, right? So by the pigeonhole principle, 2 of these numbers have the same remainder. In other words, they are congruent mod n, right? So their difference is divisible by n, right? So in other words, they are congruent mod n. So their difference is a multiple of n. Now look at these numbers. If you take the difference of two of them, you see what it looks like, right? So notice it's a number that looks like this. A lot of ones and then a lot of zeros. Is that okay? Does that make sense?
Yeah.
Yeah. So you look at all the numbers that have only, which are written down only with ones, okay? And if you take n plus one of them, two of them will have the same remainder because there are only n possible remainders. Pigeonhole principle says two of them must have the same remainder. So their difference must have remainder 0. In other words, the difference is a multiple of n. And what is the difference of two of these numbers? Well, if you take the whole bunch of ones minus a little bunch of ones, it's ones and then zeros, right? So in fact, we could have stated the theorem, if you wish, in an even more precise way, where in fact, if you take any number n, there is a multiple of n, which is of the form a bunch of ones followed by a bunch of zeros. Okay. Okay, so that's, I mean, we're going to do one which is really fancy after, and it looks a little bit like this one. It's a bit similar. But before I do fancier examples, I'm going to give you a slightly more general version of the pigeonhole principle. But it's the same idea, but it's just it quantifies a little bit more how many you can have in a box. So depending on how many objects you put in these boxes. Okay, so here is a slightly more general version of the principle. Okay, before I state it, I'm going to try to explain it or to justify it, and then I'll state it. You'll see how it works. Okay, so suppose we have n objects and k boxes, and I place these n objects in the k boxes in any way whatsoever, and I'd like to make sure that there is a box which contains at least so many objects, right? So we know that if n is k plus 1, if you place k plus 1 objects in the k boxes, however you do it, it's not possible to place one object in each box and you're done. It's just not possible to do that. There will be a box with at least 2. But suppose you had like a lot of objects, then you'll say, but there must be a box which is going to contain at least so many. So can we quantify this? So here's the trick, or a trick to do this. So take the division algorithm. I mean, this is the way I find it easier to understand the next result. If I just state it, it's just like I have trouble with it. It's not immediate to me, but if I think of it in this way, then I find it obvious. Okay, so by the division algorithm, n is equal to q times k plus r, where r is, so I'm dividing n by k, right? So I have these boxes. K boxes. And I'm going to place N objects into these K boxes. So imagine that you're placing Q objects in each. Look at it's N is QK plus R. If you place Q objects in each box, you'll be left with those R, right? And you'll have to place them somewhere. If R is 0, okay, so let's argue this way. So suppose first that R is 0. So K divides N, or N is a multiple of K. Then certainly you'll have one box with at least Q objects, right? Then there exists a box with at least Q objects. Does everybody believe me? Since N is equal to Q times K, if I don't put Q in each box, that there must be a box with at least Q, because otherwise I'm not going to reach. And it's the same argument as for the basic pigeonhole principle with Q equals to 1. Okay. Now, if R is bigger than 0, right, then think of it again this way. So there's you have Q objects that you can place Q objects in each box, and you still haven't reached N, so you're going to have to add something, right? So it means that a box will have to contain Q plus 1 objects. So then there exists a box with at least Q plus 1 objects, for sure, right? Because otherwise each box contains at most Q, and then I'll have at most K times Q objects, but N is Q times K plus something else. So it's not possible. So does everybody believe the statement the way I made it? Yes, good. Yeah. Okay, so I'm going to translate that in a more compact way. So this is not compact, but I find it easy to understand. That's the proof of what I want to write down. Now, it turns out that this Q in this context can be written in terms of N and K only. So notice that if R equals to 0, right, then this Q is equal to ceiling of N divided by K. I mean, it's actually exactly equal to N over K, right? But in particular, it is ceiling of N over K. And if R is bigger than 0, Q plus 1, that is ceiling of N over K, right? So what is ceiling of N over K? You divide N by K, and if it's an integer, but that would be the first case, but if it's not an integer, then you bump up, right? But look at this, N is equal to QK plus R. If R is bigger than 0, then N divided by K will be Q point something. So Q plus 1 is the ceiling of N over K. Okay, so now I don't need to distinguish the case R is 0, R is bigger than 0. Here is the more general version, which I've just proved. So this is a pigeonhole principle general version. So if N objects are placed in K boxes, there is a box containing at least ceiling N over K objects. Okay, so this is what I proved. Okay, so proof above. It's not the proof that it's in the book. If you don't like my proof, if you have no clue what my proof is doing, then you can go and read the one in the book. It's completely different. Okay, so my way, this is the way I understand it well. Okay, so here's an example of how this can be used. If I have 100 people, okay, I'd like to know how many for sure are born the same month. So there are 12 months. Okay, so this pigeonhole principle says that I'm going to have at least ceiling of 100 divided by 12, which happens to be 9. So at least 9 people are born the same month. Okay, for sure. You can see it backwards if you wish. If you have only 8 people for each month, then 8 times 12 doesn't get to 100. You're not going to reach 100 with only 8 people born in each month. So there must be some month with at least 9 people in it. Okay, so that's the same. So here's another one, which is same idea, but again, you don't really need to. You can sort of figure it out on the fly. It's the overall principle which is interesting. So here's the question. So what is the minimum number of students in discrete math discrete math class to make sure at least 6 get the same grade. So here grade is A, B, C, D, E. There's no F. Okay. So what is the minimum number of students in discrete math to make sure that at least 6 will get the same grade? Now you can use this formula we just developed, but I mean, it's the same thing, but basically I see it negatively, right? So suppose, what's the worst case scenario you can imagine is you have 5 students in each grade, right? A little bit like I said for the months and the birthdays, right? So if you have 5 people that getting an A, 5 get a B, 5 get a C, 5 get a D, 5 get an E, you have 25 people, and this will not occur. So it means that if you have 26, then you're sure it's going to work out, right? So 26 because, okay, see above, 26 divided by 5, ceiling is 6, but 25 divided by 5 ceiling is 5. That's bad. Okay, which I just wrote it this way because it's quicker. But basically it's just simple reasoning, right? If you have 5, the worst case scenario is that 5 people get the same grade for all the grades, and you're stuck there. That's 25 people, and you're going to get 6 with the same grade. So that's it. Okay, that's not very deep. Okay, which doesn't mean that sometimes some mornings we just don't get it. Here's another one, and then we're gonna hit some trickier ones. Okay, we have a regular 52 card deck. I'm presuming everybody knows what a so-called regular 52 card deck is. There are 4 kinds of cards, right? So spades, hearts, diamond, clubs, right? And for each one of them, there's 1 to 10. Then there's a jack, a queen, a king, and an ace for each, right? For a total of 52. Okay. So the questions are, these are called the suits. 4 suits. Okay. Question A. How many cards from a regular 52 card deck must be chosen to make sure at least, okay, so wait, I don't want to write this twice. So how many cards minimum chosen to make sure at least 3 of the same suit, and B, at least 3 of hearts. So these are, there's no 1 in a card. Oh yeah, that was my ace. Yes, that's true. Yeah. Thanks. Yeah. Ace is a 1. But I put it at the start and at the end, which if you've never seen a card deck now, you're totally confused. But I'm presuming everybody's seen a card deck. Although you guys never went to CJEP. So I spent a great deal of time playing cards when I was in CJEP. Yes.
No, I think we all went to CJEP.
Yeah, I know.
One
We
semester
went
and
for a
half.
semester and a half. That
Yeah,
counts.
that's right. Yes. Yeah, you did. Okay. Yeah. Okay, so yeah, I should have been going to math class, but I didn't. Don't listen to me. Okay. Yeah, so I want to make sure that I have at least 3 of the same suit if I take that many cards. So again, I'm going to work it backwards. If I don't have 3 of the same suit, that means the worst case scenario is I have 2 of each. So that's 8 because there are 4 suits. So from 9, I should be okay. So for A, 9, because, well, 9 divided by 4, ceiling is 3, but 8 divided by 4, ceiling is 2. That's the reason, right? B is a bit trickier. It's different. I want not only 3 of the same suit, but I want actually to make sure that when I take that many cards, I'm guaranteed always to have 3 cards, which are hearts. Does anybody want to?
Suit?
Suit, sort. One of the 4, not colors, because there are 2 suits of each color.
Okay, to have three of the different like to have at least like 1 spade, 1 heart, 1 diamond.
No. I want a suit. I want to make sure. So are you talking about question A?
Yeah, because I
Okay.
don't really know like cards game. So what is it?
Okay, yeah. There are 4 suits. There's hearts is a suit, spades is a suit, diamond is a suit, and clubs is a suit.
Okay.
They're just 4 families. They have a little symbol, which is the same little symbol.
Okay, we just want to make sure we have at least 3.
3 of the same.
Okay,
yes.
Okay.
Yeah. Yeah. I mean, all you need to know is that there are 4 suits. That's all. Now, for the second question, I want to make sure that I not only do I get 3 of the same suit, but always 3 of hearts. So I take any bunch of cards, that many. I'm looking for the number that many. And I want to make sure that if I take that many, I'm always guaranteed to have at least 3 hearts appear. Does anybody see how to reason that one out?
You would have to take the worst case scenario where you get all 12 cards for the other suits.
Yeah.
So 12 cards for, we want hearts here, so 12 cards for spades, 12 cards for diamonds, 12 cards for clubs, and then 3 more cards for
Yeah, so it's 13, but yeah, that's exactly it.
13,
right?
so yeah.
Yeah,
So.
yeah. So exactly. So the worst case scenario is you get 13 spades, 13 clubs. I'm not putting them in any order here, and 13 diamonds and 2 hearts, right? If this is a possibility if you pick 3 of each suit is 12 cards picked. Are you talking about, Mark, you're talking about A? Yeah, no, so we just want to make sure that there's at least 3 in one suit, not in all of them. Yeah, exactly. Oh yeah, some, I should read this better, of some suit. Yeah. Yeah, so in B, the worst case possibility, I mean, it's possible to have that many cards that you take without having 3 hearts. So how many are there? That's 41. So it is possible to pick 41 cards without having 3 hearts, right? But if you pick 42, then you know you're okay, because if you have 42, okay, so 42 must be good, but let's argue it. Let's just to make sure. All I've said is 41 is no good, but maybe 42 is no good. I have to make sure it is. So 42 is good because if no 3 hearts, right? The best. So if you look at what remains, so the remaining cards force this whole thing. You'll have to take all spades, all clubs, all diamonds, and 2 hearts, but at least 3 hearts, right? It's impossible to have 42 cards without having 3 hearts. Okay. I should actually point here like this. That's better. Okay, so 42 is the number you're looking for. If you pick any 42 cards, you know that you have 3 hearts in those 42 cards. Okay, at least. That's boring. Okay, here now is a several, but so I'm going to do now 3 very, very sophisticated applications. The first one is longer, but not, I mean, it's really cute, but it's sort of weird. The other 2 I find more interesting, but they're shorter. So now let's take a look at, so 3 clever applications of the pigeonhole principle. By application, I don't mean to the chemistry, but examples of use. So here's one. I mean, this one is like it smells of, it looks like it was designed to make everything work, but it's still pretty cool. I have to say that it's really, really cool. Okay, so we have a baseball team, and they play they play games, baseball games, during a 30-day month. And they play at least once a day. So it's not a real sport, so they can play at least once a day. I'm joking, I love baseball. At least once a day, but no more than 45 games. Okay, so we have a baseball game, a baseball team. They will play during a 30-day month. They will play a certain number of games, which is at least once a day. It could be more. They could play double headers, triple headers, whatever, but a total no more than 45 games. And we are asked to prove that there exists a sequence of consecutive days where they play exactly 14 games. Okay, like this problem is slightly cooked up for the numbers to work and all that, but it's still pretty cool. I mean, it's like, well, if you've done math competitions, you may have seen problems like this before. It looks like a math competition problem, not necessarily an easy one. And if you don't know the pigeonhole principle, I don't know how you can do this. I really don't know. But even if you do know the pigeonhole principle, you have to set things up to do this properly. Now, think back to the problem we solved earlier where we found a multiple of n with only ones and zeros. And what we did is we took a bunch of numbers with ones and we subtracted. So we're going to use something a little bit similar here. Okay. So, so again, so basically what you're doing is you have a calendar with 30 days and you're going to schedule games during these 30 days with the rule that there's at least one game per day and a total no more than 45. And you have to prove that there is a sequence of days somewhere that will give you 14 games. Now think about it, I mean, if you try to brute force this, you will die of old age before you figure it out, right? There's just way too many possibilities. So you want to find a shortcut. So I could leave you thinking about this for a while, but I mean, that's not the point. The point is for me to show you some tricks. So here's the solution immediately. The first trick is a very smart and useful one, and it'll give you the right direction, and it is this. Rather than looking at the number of games played on each day, what you do is you consider the number of games played from day one up to day I. Okay, and I will tell you why this is so smart. Okay, so let AI be the number of games played up to day I. Right, so A1 is number of games played on day one. A2 is number of games played on day one and day two. So you're looking at that. Okay, if I'm looking for consecutive days where I have exactly 14 games, in terms of these numbers, what am I looking for? I'm looking for the difference of two of these numbers to be 14. That's exactly what I'm looking for. So notice we want to show that there exists I and j such that aj minus ai equals to 14. That's the first observation. Hopefully you right. So if you're counting all the games from day 1 to day J and day 1 to day I, you subtract, that means you get the number of games from day I plus 1 to day J, right? So consecutive. So if you look at those numbers and there are 30 of them, right? You want the difference between two of them to be 14, which is like super good. And then, well, we still haven't solved it. Okay, so why would the difference of two of these numbers be 14? So that's the first ingredient. Second ingredient. So look at the numbers A1, A2, right up to A30. These are positive integers, and it's an increasing sequence because they have to play at least one game per day. This is an increasing sequence of positive integers, right? So they have to play at least one game played each day. Okay, so it guarantees that these numbers are actually going up. They have to increase. Okay. Now, here is now the next really super important thing to do. And I don't know how you come up with this. I don't think I would have come up with that. Not this way anyway, but look at the sequence of all these numbers and you add 14 to these numbers. Okay, so A1 plus 14, A2 plus 14, right up to A30 plus 14. Now, if I started with a sequence of an increasing sequence of positive integers, I still have also an increasing sequence. So this is also increasing, right? Obviously, there are no two numbers which are the same. They're getting bigger and bigger. Okay. Well, we're still not done. Okay, but we're almost there. Okay, so what have we not used yet? It's the hypothesis that the total number of games played is at most 45. Okay, so now these are 60 numbers between. So what's the smallest possible number? It's 1, right? The first day you can play just one game, possibly. What's the biggest number in this whole list? What's the biggest possible number?
59.
59, yes. Ooh, and if you're doing this as a problem and you see this and you go, okay, I know I got it. For sure, now we've got it, right? Because I've got 60 numbers between 1 and 59. Pigeonhole principle says two of them are the same, right? Pigeonhole principle implies two are the same. Now, that 14 is, I mean, we hope that works, right? So look at those first 30 numbers, A1, A2, right up to A30. They're all different, right? We said it's an increasing sequence. They are all different. Same for the next 30. I mean, I'm not saying they're in order, I'm just in my list. So A1 plus 14 right up to A30 plus 14, these are all different. So if the first 30 are all different, the next 30 are all different, and I have two which are equal, they have to come from the different lists. Okay, so since this and this are increasing, means all different, right? It means that there exists an AI equal to some AJ. I should have written, I'll write it the other way, so it'll match what I wrote earlier. AJ equals to AI plus 14, right? One of those, so none of those 30 in double star can be the same. None in the star can be the same, but in the whole list of 60 numbers, 2 must be the same. So there's 1 in the first list, which is equal to 1 in the second list. We're done. Yeah. So again, this is a problem where if you've seen one and you think about it a little bit, you say, okay, I've seen it. I figure out how it works. So if I asked you to do a similar one, it wouldn't be a nasty question. But if I had asked you that question without you having seen it before, that would have been a very, very, very nasty question. But easy to mark, though. I'm sorry, I'm kidding.
Yeah.
Yep.
I have a question.
Yes.
Where does the 1 in 59?
Yep.
What does what does it mean?
What does it? Okay.
Like where does it come from?
Okay. Where do they come from? Okay.
Do they?
Yes. Okay. So the team, okay, that's interesting. So the team plays at least 1 game per day.
Oh, okay. No, I just
Yeah.
Yeah, it's 45 plus 14.
Yes. Yeah. Sorry.
Yeah, no, it's
Yes.
my bad, my bad.
No. But I should have written it. No, you're right. You're right. You're absolutely right. I wanted to write it and I didn't. Oh yeah, great. Use the same symbol for 2 different things. Smart. Let's do that in blue. No, I should have written that. That's the reason. Sorry about that. Yeah. So I mean, it's not the most natural. I mean, clearly this thing has been cooked up to make things work, but there are some very similar kind of situations where you have to mess around like a little bit like this. Let me show you 2 other problems which are much shorter and a bit more natural. And easier. I guess they're easier too. But that one was pretty clever. So here's one. If you take any n plus 1 positive integers which are at most to n. Okay, so imagine n is 1 million. So you take 1,000,001 integers which are at most 2 million. So from 1 to 2 million, you take 1,000,001 integers. Okay. You have to show that there is a pair of numbers in your list where 1 divides the other. Okay, so take any n plus 1 positive integers which are at most 2n. Show there exists 1 that divides another. I remember the first time I saw that, I messed around with it and I was sort of close and I just like, eh. But it turns out it's not very difficult. But again, it's not very difficult if you know how to start. So what do you do with this? Okay, so here's a trick. So let's say I have my numbers A1, A2, right up to AN plus 1. Okay, these are the numbers, then they are all between 1 and 2n. Okay, now obviously you can make some I mean, let's say you're given a problem like that. You have no idea where you're starting. You just start messing around, and it's not bad to actually look at some examples and to try. And you have to get your hands dirty. You have to really, get a feel for it. Unless you see the solution immediately, which may happen, but I mean, obviously, if 1 is there, you're done, right? So you could always suppose that 1 is not in the list. Although it's not going to help for our solution. You can also suppose they're all different, because if the same number, I mean, I guess they mean n plus 1 positive integers. It makes no difference, because so if there's a repeat in your list, then it's trivial, right? The number divides itself. But in any case, so here is the trick. So if you use the fundamental theorem of arithmetic, you can factor all these numbers as a product of primes. Now, primes come in 2 different flavors. There's the even ones, which is 2, and the odd ones, all the other ones, right? So I'm not going to write the fundamental theorem. I'm not going to use the fundamental theorem of arithmetic full force. I'm just going to write my numbers as a certain number of times 2 times an odd number, right? So the fundamental theorem of arithmetic will guarantee this, right? So for each I, AI is equal to 2 to some power, and I'm just going to write like that. It's not proper math, but it's less tricky this way. So it's clearly, you can write every number as 2 to some power times an odd number. Hopefully everybody is okay with that. I mean, BI could be 1. It's possible, because if AI is a power of 2, then BI is 1. Okay. And if AI is already odd, then that power is 0. That's possible too. But you can always write any number as, because of the fundamental theorem of arithmetic, it's 2 to some power times whatever is left. With you take all the 2's out, you get an odd number. Hopefully everybody is okay with that. Okay, so these odd numbers, B1, B2, right up to Bn plus 1, they are among, they have to be at most 2n, right? So they are either 1, 3, 5, right up to 2n minus 1. So we're among 1, 3, right up to 2n minus 1. At this point, I would expect you to be able to finish this. So hopefully, so I've got n plus 1 odd numbers, which are among 1, 3, blah, 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 right up to 2n minus 1. How many numbers are there in this list? There are 2 ways to do it. There's the hard way and there's the easy way. The easy way, how many numbers are there between 1 and 2n?
I guess it's 2n minus 1, just numbers in that range?
Yeah, so the numbers from 1 to 2n, how many numbers are there? There are 2n, right? Yes.
Mm-hmm.
Yes. So, and there are as many odds and as many evens in that list, right? We're going from 1 to 2n. So half of them are odd and half of them are even. So how many odd numbers are there between 1 and 2n?
There are n odd numbers.
N, yes. So there are n odd numbers, right? So yes, there are n numbers here. Okay, so that was the easy way, because from 1 to 2n, there are 2n numbers, and I'm just looking at half of them, which are odd. So there are n, right? So n odd, n even numbers. Yeah, not there. Here, right? So half of them are odd, half of them are even. Because I start at 1, which is odd, and I end at 2n, which is even. So I'm counting the right. Yes. Okay. So I have n numbers, which are odd, 1, 3, 5, right up to 10 minus 1. And I've chosen n plus 1 numbers out of those. Conclusion, 2 of them are equal. At least 2 of them are equal. So by the pigeonhole principle, at least 2 of the BI are equal, right? Because I have n plus 1 of them that I'm choosing among n numbers. So 2 of them are equal. Conclusion, right? So now let's just write it this way. So BI equals BJ equals B, let's say. Okay, so AI is 2 to some power times B, and AJ is 2 to some other power times B. Is it clear to everybody that one of these numbers divides the other?
Yes.
Yes, right? So clearly the one with the smaller power to 2, so clearly one of these divides the other. Smaller power of 2, right? So because it's the same B, the odd parts. So that's the trick. The trick is just to look at the odd part of the numbers. That's where the pigeonhole principle trick is hidden right there. Okay. Did that make sense? Yep. Okay. Last example, which is really the coolest one, because there's a whole huge theory that stems from that next example. This theory is called Ramsey theory. And it's this is the point of origin of this whole theory, which is very deep, of which I should know a little bit more, but I've actually used Ramsey theory in a paper, but as a black box. It's anyway, long story, too complicated for this course. Okay, so here is my example. I have so among a group, I have 6 people. And I guarantee you that for each pair of these 6 people, sorry, they either love each other or hate each other. So there's no indifferent feelings between any 2 of these. So there's Alice and Bob, either I know they hate each other or they love each other. Okay, so among a group of 6 people, where each pair either hates each other or loves each other. Now you're going to say there's actually a theory behind, but it's, I mean, obviously we're giving silly names to the situation so that sort of makes some kind of sense. I don't know if it makes more sense. It's less theoretical. So I have a group of 6 people, and you're told that each pair of them either hates each other or loves each other. And I tell you, there must exist 3 of these people who either all hate each other or all love each other. Then there exists a group of 3 people among them that all love each other or all hate each other. Okay, so I'm going to show you why this is true. It's very short. Okay, this is really the more interesting of all the examples. There is something called Ramsey numbers, and this is an instance of the smallest Ramsey number, which is 6. And there's like an infinite family of Ramsey numbers, and they are extremely difficult to compute. Most of them are unknown. They're just way too big to compute. I know that there's been a recent results in the last year, 6 months, 3 months, a new computation of one of these Ramsey numbers, but that's not the interesting part of Ramsey theory, by the way. It's just Ramsey's theorem is a very, very useful theoretical result. And this is the smallest possible case of Ramsey's theorem. Okay, so here we go. So here's the proof. So I want to show that there are 3 people somewhere in there that they all hate each other or they all love each other. Okay, so what I'm going to do to visualize this is I'm going just to choose one of these people, just choose one person, and consider its relationship, if you want, to the other 5. And I'm going to draw this, okay? In chapter 10, which we're going to start this week, we're going to talk about graph theory, and this is really a theorem about graphs. Okay, so I have this person here, and there are 5 other people in the group, and you have these relationships which are either hate or love, right? So hate or love, each one of them, right? So I have 5 different relationships which are placed in 2 boxes, which are either hate or love, right? So I have 5 relationships in 2 boxes, hate or love. What does the generalized pigeonhole principle guarantee? There's a box with at least 3, exactly, right? So there must be 3 of these which are either all hate or all love, for sure. Okay, so pigeonhole principle says there exist 3 which are the same. Let's say, so I don't know if it's love or hate, I'll just call it X, okay? So call them X, okay? So then the situation is like this. I have my person P here, and this person P is in relationship X with 3 people. It's either hate, 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 or love, love, love. Okay, it doesn't matter, it's the same. What do you do now? What do I want to show is that there's a love triangle or a hate triangle, right? So let's consider now the relationships between these three people. Okay. Suppose that in between one of these two, there's an X. We win. Yes? Everybody sees this? Everybody is out playing. No, that's,
Wait, you said if one of them is X?
yeah, if just one of them is X, let's just do that here, right? So if, let's say this one is X, then this person, and this person, their relationships are all the same. Yes? If this one is X, then I've got X, X, X. And if it's this one, which is X, then I've got X, X, X. Right? Yeah. So if any of the dotted is X, we have our triangle. Yes? Is everybody okay with that?
Yeah.
Okay. So what's the other possibility? None of them is X, right? So otherwise, none is X. So I've got my person P here. And none of these are the same as X. They're all Y. So I've got my triangle, but then it's that bottom triangle. Yes?
Yep.
Yeah, yeah. Okay. So then all the same. So not X, but let's say Y. Okay. So if P loves all these three people, if two of them love each other, then I've got my love triangle. Otherwise, they all hate each other, these three people. So P loves these three people who all hate each other. Yes. Yeah. Makes sense? So we must have a triangle because of this. So I choose one person P, 5 relationships, 3 of them must be the same, right? I've called them X. It's either love or hate. Let's say it's love. And then the 3 people connected to those, they either all hate each other and we're done, or 2 of them love each other, and then with P we get my love triangle. Yes. So that's it. So that's really it. I'm really done. Any questions? Ooh, death.
Can I see the second proof again?
The division? Same example or which example?
The one before Ramsey's theory.
Okay, so this one.
I don't understand why BI and BJ are the same.
You don't understand why I'm just saying that there must be 2 that are the same. So I've got n plus 1 numbers, and I look at their, let's call that the odd parts. So I've got the odd parts of these n plus 1 numbers. I've got n plus 1 odd numbers, but they have to be odd numbers between 1 and 2n. There are only n odd numbers between 1 and 2n. So it means that some BI and BJ must be equal. And I just gave a name to that. I just call it B.
Okay.
You don't seem convinced. That wasn't very. It's just like, yeah, okay.
Well, I'll go see it when you post it on the books, I think.
Okay. All right. Just call them B. Other questions?